Chapter 3 is about solving a single algebraic equation f of x equals 0. In Chapter 7, we'll look at a system of more than one equation and more than one unknown, but this chapter is strictly single equation, single unknown. For example, f could be a polynomial degree 5, and you want to find the roots of the polynomial, which are impossible to do exactly. So you have to use numerical methods like the ones in this chapter. The first method we look at is the bisection method, which you may already be familiar with. It's really simple. You find 2 points A and B such that f changes sign between A and B. So you know, assuming f is continuous, that there's at least one root between A and B. It has to cross the origin to get from positive to negative. Maybe cross it several times, in which case we'll only find one of the roots, but we're guaranteed to find one of them. So you start with 2 points A and B such that f changes sign between A and B. Then you take the midpoint of A and B and you evaluate f there. And if f has a different sign from B, if f changes sign between C and B, then you know there's a root between C and B. So you move A in from the left, and now A is equal to C, and now there's a root between A and B, and you keep going. Take the midpoint each time, move the one of the endpoints into the midpoint, and keeping the change in sign between A and B. Now this is not only guaranteed to converge, but we can even predict exactly how many iterations it's going to take to converge, because the original length of the interval is b minus a. Every iteration you cut that interval by half, so after n iterations your interval size is b minus a over 2 to the nth power, and you just say, well, make that interval less than epsilon if you want epsilon accuracy. Solve for n with logarithms and you get this formula. So if you take this many iterations, you're guaranteed to have an error of less than epsilon in the final answer. So let's try it on an example. We're going to try to find the roots of the following fourth degree polynomial: x to the fourth minus 5.4x cubed, and so forth. So here's a little function that defines the polynomial of degree 4. This is just a comment up here, but we happen to know that this factors as x minus 1.1 cubed times x minus 2.1. Of course, if we knew how it factors, we wouldn't need to find the roots. Well, there they are, but we're cheating here and giving you the answer. So there are roots at 1.1 and 2.1, but notice the root at 1.1 is flat. It acts like x cubed. It has a derivative of 0 also at 1.1, whereas a derivative of f at 2.1 is not 0. So it's a flat root at 1.1 and not a flat root at 2.1. And here's our bisection program. We pass in the name of the function and our a and b such that f is guaranteed to, that we're promising that it changes sign between a and b. And here we use that formula to calculate how many iterations we need to do to get an error of 10 to the minus 12th or less. Take the midpoint of a and b each time and check if f times f of b times f of c is negative. That means that f changes sign between b and c, which means there's a root between c and b. So we move a in from the left, and now a is c, and there's a root between the new a and the old b. Otherwise we move b in. So let's try it. We have to pass in the function as with the at sign, so it'll know, MATLAB knows that's not just a variable, it's a function, and goes look for the function of that name. And let's look at the root 2.1, and let's give 2.0 and 2.15. We know there's a root between 2 and 2.15. And it takes 38 iterations, and here's a and here's b. And it's quite accurate. We know there's a root between this number and that number. They're both really close to 2.1. And so everything seems to be working fine. Now let's try the other root at 1.1. we'll take a to be 1.0 and b to be 1.15. There's a root 1.1 between there. And what happens? Well, it takes 38 iterations, which is supposedly guaranteed to give an error of less than 10 to the minus 12, and it actually only gives an error of about 10 to the minus 5, so something's wrong here. And furthermore, the root 1.1 is not even bracketed between A and B. It's both A and B are on the left of the 1.1, so something a little bit strange is happening with this root. What is it? And this graph shows what's going on at 2.1. The function does not have a zero derivative. The function itself is zero at a root by definition, but the derivative is not zero, so there's no problem at 2.1. At 1.1, you have a flat root. The derivative, not only f is zero, but the derivative is zero, which basically means there's a lot of really good roots. That's the basic problem, is there's so many values of x near 1.1, which make f really small, that it's hard to find the exact one. If f is only calculated within a machine precision, you could get a large error. I mean, you'll get an x which such that the f is small there, but it may not be close to 1.1. And we'll see that our other methods that we'll look at in this chapter also have a problem. This is every method, even bisection, is going to have a trouble with a flat root because there's so many good roots. It's hard to find the perfect one. Okay, now let's go on to the second method, which is Newton's method. And Newton's method, you approximate f. I said in chapter 1 that we were going to use Taylor polynomial to approximate f, and when you want to do something to f that you can't, you approximate it by Taylor polynomial, and whatever you'd like to do to f, you do to the Taylor polynomial. Well, we're already doing that here in this chapter. We're approximating f by its Taylor polynomial degree 1, otherwise known as the tangent line. That's the polynomial degree 1, the straight line which has the same value and same slope as f at a certain point x0. And we would like to find the point where f is 0, and we can't, but we can find the point where this Taylor polynomial degree 1 is 0. So we set it equals 0 and solve for x. And we get x0 minus f of x0, f prime of x0. So if you get the Taylor polynomial degree 1 at the point x0, otherwise known as the tangent line, and you take the point where the tangent line is 0, and you hope that's a better approximation to the point where f is 0. So the Newton's method is, if you have a approximation to the root xn, then you use this formula to calculate xn plus 1, and hopefully it's a better approximation. In fact, we'll see that it is a better approximation, at least if you start close to the root. So there's Newton's method. Xn plus 1 is xn minus f of xn over f prime of xn. Now, before we try Newton's method out on that problem and some other problems, how can we measure speed of convergence? Well, in this chapter, we define the order of convergence to be alpha such that each error is approximately proportional to a constant times the previous error of the alpha. And you can see that the bigger alpha is, the better, because assuming it's converging, the error is small, then you raise that to higher power. That makes the next error really small. So the order is going to mean something a little different in other chapters, but in this chapter, it's the power of en that en plus 1 is proportional to. And we're going to get some theory about what the order of these methods are. Bisection method, you can already tell that the order is 1 because each step, the new error is approximately 1/2 times the previous error to the 1 power. So bisection is only first order. We'll see that Newton's method is normally second order. But we can calculate an experimental order, except we're going to need 3 consecutive errors because there's 2 unknowns here, m and alpha. We're interested in m, but we're mainly interested in alpha. So how can you solve for alpha? Well, experimentally, you can use 3 consecutive errors, en minus 1, en, and en plus 1. That en is xn minus the true root, of course, the exact error of xn. That's the exact error of xn minus 1. So if you know 3 consecutive errors, you can divide these two and you get rid of the m, and then take logarithms and you can solve for alpha. So here's the formula that we'll see for approximating the experimental order. It's only approximate because this is not exact here. It's presumed to be exact in the limit as you get close, but you get round off error when you get too close. Anyway, this is our experimental order of convergence, and without knowing anything about the theory, you can approximate the order, the speed of convergence of a method, and that's what we're going to do. Okay, so let's apply Newton's method to this polynomial degree 4, the same one that we just used for bisection. Again, it has roots at 1.1 and 2.1, a flat root at 1.1. And Newton's method needs the derivative. That's one of the weaknesses of Newton's method. It assumes you know the derivative. Well, polynomial is pretty easy to take the derivative of. There it is. So each iteration, new x is old x minus f of x over f prime. And I'm going to stop if the error is less than 10 to the minus 12. And here we're calculating the experimental order using that formula we just showed. So we pass in the initial approximation and the true root. So, only thing we use the true root for is to calculate the error so we can see how fast it's converging. Normally you don't know the true root, of course. So let's start close to the root at 2.1. Let's just do 2.0, and 2.1 is the true root. And it converges quite fast. The error after, well, we're only doing maximum of 10 iterations. It's already down to an error of 10 to the minus 8 after, 4 or 5 iterations. And notice the experimental order of convergence appears to be about 1.99. So that's our experimental order of convergence. It's converging very fast. 2 is very good. That means, you can see it's almost exactly 2.1 after however many iterations this is. That means that each iteration, the error is proportional to the square of the previous one. So once the previous error gets small, it really gets small with the next iteration. Now let's try to find the other root at 1.1 that bisection had trouble with. So let's start near 1.1. The true root is 1.1. We start at 1.0. This time it's converging very slowly. It's supposed to be at 1.1. It's 1.098 after 10 iterations. So the error is quite large, and the order is only 1. So it seems to still be converging, but the order of convergence is only 1, which is not nearly as good as second order. That means that each error is proportional to the previous error to the 1 power. So it's having trouble with that triple root, that flat root, as bisection did. So now let's try Newton's method on a different function, namely x times e to the minus x. And that obviously has only one root at x equals 0. But x times e to the minus x goes up, and then it reaches a peak at x equals 1. In fact, here's the derivative of, you're going to need the derivative for Newton's method. You can see the derivative is 0 at 1. So it reaches a peak at 1, and then it starts to go back down. So let's see what happens. You might suspect that if you start to the right of that peak, things are going to go badly because the tangent line is going to be pointing out to infinity. So let's try starting at 1.5 to the right of that peak, and x is out to 13, 14. It's basically going off to infinity. It keeps thinking must be a root out there at infinity, but never is. So this illustrates that Newton's method is not guaranteed to converge. If you start close enough to the root, for example, in this case, if we start close to 0, Well, it converges real fast. The order is second order again. So Newton's method typically converges real fast if you start close to the root, but if you start too far away, anything can happen. It might go off to infinity, it might oscillate forever, it might converge to another root. Basically, any smooth function looks like a straight line through a microscope. So if you start close to the root and you're approximating the function by a tangent line, that's a very good approximation close to the point. So it's going to converge real fast if you start close to the root. If you start too far away, anything can happen. So it has the disadvantage over bisection method that it's not guaranteed to converge, but when it does converge, it converges very fast. Okay, a couple of interesting applications of Newton's method. It says that Newton's method is actually used to find the square root of a on many computers. How would you find the square root of a? Well, if you just solve x squared minus a equals 0, the root will be plus or minus square root of a. So presumably if you start with a positive x, it'll converge to the positive square root. And if you simplify Newton's method, just put f equal to x squared minus a and f prime to be 2x and simplify a little, you get this formula here. And so this should converge, at least if you start close to the square root of a, should converge to the square root of a. Let's try that out. So here's another program that applies Newton's method to solve x squared minus a equals 0. And of course the true root is the square root of a. We're only using that to calculate the error. So we'll pass in a starting value and the a that we want the square root of. And each iteration we just have x equals 1/2 x plus a over x. That's Newton's method simplified a little, just like we showed. And let's see what happens when we try to find the root of square root of 3, which is about 1.7. So let's start at 1.5. And it converges very fast, second order again, to the root of the square root of 3, which is about 1.732. So this is actually a very efficient, only a few iterations, very efficient way to find square roots. But you want to make sure it converges. If you're going to, design a calculator button so that when you press the square root button, it solves x squared minus a equals 0 with Newton's method, you better hope it converges. It'd be embarrassing to have a error message say square root of 3 and it comes back with does not converge. So how close do you have to start? Well, let's try a little experiment here. Let's try 0.5 to find the square root of 3, and it still converges fast. Let's try 5. Remember, the true root is 1.732, and it still converges. And we can actually show that it's actually going to converge to the square root of a for any positive value of x. Of course, the closer you start, the quicker it'll converge. So that's an important application. That's where you could use bisection method, but you want it to converge fast when you're calculating square root, because you may be calculating lots of square roots. Another interesting application. Now remember, computers can only add, subtract, multiply, and divide, but when you use Newton's method to solve x squared minus a equals 0, you're not doing anything except add, subtract, multiply, and divide. So it wouldn't do any good if you have to calculate square root of x in calculating the square root of a. So that's a way to calculate the square root of a without cheating and just using add, subtract, multiply, and divide. Well, some computers can only add, subtract, and multiply. They can't even divide. Some early computers, and in fact they say even some present-day supercomputers. So if you want to divide a by b, and you have a computer that can add, subtract, and multiply but can't divide, what do? Well, if you could find 1 over b without doing any divisions, then you just take a times 1 over b. So how can we calculate 1 over b? Well, we apply Newton's method to b minus 1 over x equals 0. And if Newton's method can find the root, of course the root will be 1 over b, which is what we want. However, we have to do Newton's method in such a way that there's no divisions. Well, the derivative of this elf, so we apply Newton's method to this elf, b minus 1 over x, knowing that if it converges, it'll converge to 1 over b. The derivative of minus 1 over x is 1 over x squared. So Newton's method, there's our elf and there's our elf prime. Well, there's 3 divisions there, so this is no good. We're trying to avoid, we're trying to do this on a computer that can't divide, so that's no good. But if you simplify, you can actually get it down to where there's no divisions, x times 2 minus bx. So this is only add, subtract, and multiply. So if this converges, Newton's method will have found 1 over b without dividing. So here's a Newton's method applied to the function b minus 1 over x, or a minus 1 over x. I'm using a instead of b here. And there's the iteration we just saw after simplifying to where there's no divisions. I've got a division here, but that's just to calculate the true, so I can compare, but we're not, Newton's method doesn't actually use any divisions. And should be able to find 1 over a starting with x0. So let's try to find 1 over 3. Let's start from, well, it's going to be 1/3, so let's start with 0.3. And it converges rapidly to 0.33333. Let's start a little further away. Start at 1. Well, that doesn't converge. In fact, it goes off to infinity, basically. So there's a danger here that if you want to find 1 over a, you have to start, turns out you have to start within 100% of the true value of 1 over a. In fact, the book shows that your starting value had better be between 0 and 2 over b. In other words, between 0 and twice the true 1 over b. And if you start within 100% of the 1 over b, the root 1 over b, then you're okay. But if you start outside that, you're in trouble. Well, it shouldn't be too hard to have an initial guess that within 100% of 1 over b, so that is probably not a problem. Okay, we saw experimentally that Newton's method was second order, that is, the error each step is proportional to the previous error squared. Here alpha is the root, what I'm calling r, and that's what I'm calling alpha, but they show in this section theoretically that the Newton's method is indeed second order, that is, the error each step is proportional to the previous error squared, assuming that f prime is not 0 at the root. So at that fourth degree polynomial near 1.1, it was the derivative was 0 there, and we had trouble, so it's not clear what happens when the derivative is 0 at the root, but at least you can prove that the error is second order if the derivative is not 0 at the root. We're going to prove this, but later in section 4 when it's a little easier to prove. So Newton's method is faster than bisection. It has a disadvantage that you need to supply the derivative, which is not a problem for the functions we've looked at, but for other functions it might be a problem. And it's not guaranteed to converge, so you have to make sure you start close enough to the root. And the method of the next section, secant method, is basically designed to avoid the first problem of Newton's method where you have to supply the derivative. So it's a way to approximately apply Newton's method without having to supply the derivative.